is called a reflection coefficient, or S11 in S-parameter language. And the same we would do, we will wait for the output at the other end, and we would get the transmission. And with a reflection and transmission mapped, we know all the construction parameters to have this as a circuit element, a filter that we can manufacture first, design, then manufacture, and then sell. But anyway, how to do that? Again, for example, our old method of feeding anything to here, this used for the cavity, would not work. If I just suddenly change one value over here, so I am not getting the TEM wave that propagates as a plane here. I would get something radiating in all directions. This something at the input would not be the TEM wave, so it would reflect back, and I will not have a good solution. So how to do it more properly? Well, first, I would like to know the transmission of the TEM mode, and therefore I should somehow do a TEM feed to the structure. In order to do that, I can supply a field that belongs to the TEM field. Just remember from the basic course of electromagnetics, the field in a coaxial structure has, for the basic TEM mode, two components. There is a radial field, E radial, which is given by the charge sitting on the inner conductor and some constants, and more or less it is some E maximum divided by radius. So the field decreases with the radius from the center of the structure, is inversely proportional to the radius. And there is a magnetic field. For this case, if I have E in this direction, the magnetic field would point out in this direction to get propagation that way. And the magnetic field is circular around the central conductor, and again there is some magnetic field maximum divided by R. So both field components are inversely proportional to the radius, and both of the field components can be calculated for a given wave. So what we can do now is to feed the structure not in one point but in one layer. So we have, for example here, we select a set of field values. We have the E radial components of the E, and in order to feed it, we put their field values at inversely proportional rate from the center. So we have feeded the structure by electric field that is proper to the structure. And just imagine we do only a feeding by the electric field. What would happen then? Well, it would propagate into both directions. So if we put such a feeding there, so let's make a one-dimensional cut, we would have at the beginning of the feeding value. A little bit later, we would have, for example, set a pulse. We would have two pulses there, one and the other. This is propagating there, and this is propagating there. This would happen if we do not put there a proper magnetic field, because in this case we fed the structure by a superposition of two pulses just going in opposite directions. They had the same directions of electric field and opposite directions of magnetic field, which made 0, and therefore we invoked 2 pulses. In order to get 1 pulse only, we would have to also feed the magnetic field, just we would have to remember that the magnetic field is sampled 1/2 step ahead or behind, and therefore we have to shift it a little bit in time. So now we are able to put there electric or magnetic field. We know that feeding the structure with an infinite pulse would be a problem because we would violate the Courant condition. Such a pulse would be not bound in frequencies and would contain frequencies that the net would not represent correctly. So now we have several possibilities. For example, we could feed the structure by a time-dependent feeding that is sine or cosine, so single frequency, and that would work. But how to make a good feeding for the structure which is containing a lot of frequencies so that we can run several frequency simulations in one time simulation and not exceed the Courant condition. And there are several solutions for that, of course. So first, what we really are seeking for, well, we would like to have a signal that feeds the structure and in frequency domain. The signal should be rich in components, so it should contain DC, it should contain the basic frequency, it should contain all the frequencies that are interesting to the calculation and that satisfy current condition. So we have made sufficiently fine space and time cuts to represent that frequency. But it should not contain any other frequencies. So the ideal signal would be something like a rectangular pulse. Well, there is no physical representation that is easy to find out in time domain for this. So we will really use an approximation to feed this something that contains frequencies like this graph would be also nice. So this is something that more or less contains a lot of frequency, a lot of energy at frequencies up to a certain boundary, and then it drops fast down. So this is how the signal, be this energy, be this electric field or magnetic field, but how the signal should behave as to its Fourier transform. But the question is how that would look in time domain, because we have to feed the structure in time domain. And more or less there are 2 signals that are quite similar to each other that are used. The first of those signals is a Gauss pulse. So the signal as a function of time is some magnitude times e raised to minus t lomeno a, where a is a constant, squared. Now this has in frequency domain a shape like this. You possibly know this function from probability calculation, is the Gauss distribution, and that would be, let's say, the variation. Now, by changing the A parameter, you could widen the pulse, and the wider the pulse would be, the lower would be the frequency at which you experience a sudden drop in energy or electric field components. So by the constant A, you might change the width of the pulse and the frequency content. And there is another way how to move, of course, the pulse. If you substitute t by t minus t0, then you shift the pulse to another time, because this pulse runs in negative times either. Well, this is a very often used type of feeding. It has one disadvantage, well, not very big. If you really run to precise calculations, you might mind that there is a problem. This function, this exponential, is non-zero for any t, for any time. Well, that's not very nice, because in fact it has been there also at the time. It should have been, the pulse should have been calculated and propagating in the structure even before you started the calculation. Well, in reality, this makes only a small difference, which is under the other errors in your calculation. But let's say, okay, is there any other option that is used? And the second pulse that is used quite often is developed or constructed by Blackman and Harris. And it's a signal that is artificially constructed, but anyway, it's constructed so that it has several important properties. First, we take a window and we define that our signal would be zero out of it. So the signal would have non-zero values only within a certain time window. Then we construct a series of sine signals inside, so that the first of them would be 1/2 sine wave, just running from zero at the beginning of the time window, reaching maximum at the middle, and getting to zero again at the end of the time window. This is a piece of harmonic signal. If we cut it and have only this half wave, it would anyway contain a number of harmonics. But it's not enough. First, Blackman-Harris not only insisted on zero value at the ends, but also on zero derivative against time. Now, this is not possible to achieve with one sine, but if you add a third harmonic, so a signal like this, and a fifth harmonic, which I will try to plot in black, so you have 3 harmonic components, and then you can combine them. And you can combine them, all of them are have inherited the property that they are zero. The function values are zero at the ends of the window. So that's fine, we have the zero value. but then we can use them and combine them so that the derivative at the end is also zero. Then we mix several harmonics and finally it gets a shape which is very similar to the Gauss pulse. You would not distinguish that by your eye, but has zero derivatives at the end of the window, which then generates less stress on the numeric net. So this is something that is used. A Blackman-Harris pulse or a Gauss pulse. Both signals are very similar in shape. Both signals have limited harmonic component content when transformed to frequency domain, and by setting the window more or less wide you get higher frequency or lower frequency. That is the switch between a rich component and low component, which is the division between, let's say, uniform content of frequencies and low or decreasing energy in frequency band in the signal. So you can get a good feeding signal. Now you have this dependence on time. You multiply that by the space dependence of the signal, which is maximum divided by radius, and you feed this into the structure for a limited number of steps. And in this manner you fed the structure with only frequencies that the structure is capable of handling. You fed it with the signal that is proper for the coaxial cable. So you get only signal propagating in that direction. Remember that we have put on both ends a non-reflecting condition that we have described earlier. And now we have a signal that runs in. We have a signal that reflects from the discontinuity, and we have a signal that makes it through the structure. So we have to record all those signals, input, reflected, and gone through, and we record them in time. So we would have an input signal, we would have the output signal, and we would have a reflected signal. Now, although those all signals are functions of time, in fact what we will get is a set of values at time steps. So, in fact, those are functions of time, but what we get are vectors of values at different time step numbers. So we have a vector of input signal, output signal, and reflected signal. Now we can Fourier transform each of those values, and if we do that, we will have a result. So, for example, scattering parameters S11, the reflection coefficient, which is a ratio of incoming and reflected wave, would be obtained like a fast Fourier transform of the reflected signal divided by a fast Fourier transform of the incoming signal. As those are vectors, if we divide, this division would not be very liked by mathematicians. But what I mean by this is that each of the components of this vector is valid for one frequency, and the scattering parameters for this frequency could be obtained by dividing nth component of the reflection by the nth component of the incoming signal. So we will have a vector of S11 at frequency 1, S11 at frequency 2, and this would be the vector of values of the reflection at all frequencies we have studied by the simulation. In this manner, we could get, by running one time domain simulation, then we get covered the behavior of the element in the whole frequency span. So we decide to have discretization in time and space sufficient, for example, to cover the frequencies up to 10 gigahertz. Then we run the simulation and we get fast Fourier transformed the signals, and we get up to 10 gigahertz the frequency characterization of the parameters. And the same could run for the transmission, that is S21 in scattering parameters language. So we would have first done the Fourier transform of the output signal divided by the Fourier transform of the input signal, and the division is done member or element by element. So we get a vector which is then the scattering vector of scattering parameters at distinct frequencies along the frequency band we sought to solve the structure for. Now this possibly invoked some questions. May I ask you 4 questions?
And we have to wait for convergence to happen before we